Hi, my name is Silvana Aristizabal, and this is my lab report for Lab 4 on oscillations. Here's the table of contents of what we're going through in this presentation. Firstly, the introduction. The overall purpose of this assignment is to observe, analyze, and model the oscillatory motion of a spring mass system, compare observed position from video analysis with the predicted position from a computational model, and we will achieve this using three main tools: Tracker for video analysis, GlowScript for building the computational models of the spring mass system, and spreadsheets for storing data and plugging into Tracker. All of this helps us gain a deeper understanding behind Newton's second law of motion and the energy principle. So let's explore more about these fundamental principles. Firstly, the momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here how by deriving from the momentum principle, we can obtain the velocity update formula. This formula allows us to determine the object's velocity at each timestamp when dealing with a non-constant force. In our computational model, we use Newton's second law, where the net force is equal to the rate of change of momentum. For a spring mass system, the net force has two parts: the force from the spring and the gravitational force. The equation we can see in the slide. The energy principle states that energy can be created or destroyed, only transformed from one form to another. In our system, which includes the spring, mass, and earth, there are no external surroundings doing work or adding heat, so the total energy stays constant. That means that the change in total energy of a system is zero. Mathematically, we write this as the equation in the slide, which just means that the energy moves between kinetic spring potential and gravitational potential, but the total doesn't change. So for our procedure, we first uploaded a given video of a spring oscillating to Tracker to record position at each timestamp. Based on the X and Y position gathered from the video analysis, we created a computational model of the mass's motion on GlowScript. We calculated and analyzed kinetic energy, gravitational potential energy, and spring potential energy using X and Y data copied to a .csv file. Then we analyzed final results and discussed the findings. Now let's take a look at the actual motion we analyzed. Here is a video of the mass oscillating. By examining its motions frame by frame, we collected trajectory data. With the data we collected, we were then able to construct a computational model of the motion we observed. So firstly, to build a computational model from Tracker, we know the starting X and Y position. We also were given the mass, so we plugged it into Tracker. Before running the simulation in GlowScript, we needed to calculate two key initial conditions: the spring constant K and the relaxed length of the spring. On the left, I used the period of oscillation from the Tracker data and plugged it into the formula to calculate the spring constant. On the right, I calculated the relaxed length using the equilibrium condition, where the upward spring force balances gravity. I then plugged both of these values into GlowScript code to make sure the model matches the physical system as closely as possible. In this part of the code, we define the key components that describe the motion and energy of the system. The first three lines in blue calculate the spring vector L, which goes from the fixed point to the mass. Then we get the unit vector L hat for the spring's direction, and S, which is how much the spring is stretched from its relaxed length. Below that in purple, then we calculated all the system's energy at each timestamp. For this step, we first defined the initial energies, then we calculated the gravitational force, we calculated then the spring force, then the net force, and finally we applied the momentum principle to update velocity and position. For this part, we then updated the spring, and then we calculated the energy changes for kinetic energy, gravitational potential, spring potential, and then the total energy change. By running this code, we get these graphs. Here, we're comparing the motion from our computational model in blue to the actual motion of the Tracker video analysis in red. On the left, we see the X position over time. The model and experimental data follow a similar pattern, but there are small differences in amplitude and timing that we will later discuss. On the right, it is the Y position over time, and again, we see a close match in the overall shape, but the experimental motion seems slightly more abrupt. This might reflect to some small inconsistencies in the video tracking, etc. Overall, the trends line up well, which shows that our model captures the key physical behavior of the spring mass system, even though it's not a perfect match. So let's take a look at the actual possible sources of error in our experiment and how they may have affected our results. Firstly, human error when conducting video analysis when tracking each timestamp, then rounding errors, camera misalignment, and dismissing other external factors, environmental factors who could have affected our final graphs. Now, to reflect on the overall experiment, we can answer these questions. Now we have to compare the oscillation periods depending if we're using the X position or the Y position data. So Basically, we get that using different directions affects the key spring constant and the overall graphs. This highlights how the direction of motion and forces involved affect the observed behavior of the system. Thank you.